Individuals make decisions based on expectations of outcomes in the context of incomplete information and limited capacity to assess and process information that is available. Thus, people develop heuristics, which are shortcuts for figuring something out, like always choosing option C. Often, these shortcuts manifest as irrationalities or biases toward one option as opposed to another. Keynes had this to say about those irrationalities. Most probably of our decisions to do something positive, the full consequences of which will be drawn out over many days to come, can only be taken as a result of animal spirits, of a spontaneous urge to action rather than inaction, and not as the outcome of a weighted average of quantitative benefits multiplied by quantitative probabilities. In this segment, I will be attempting to corral the animal spirits into something like a taxonomy. We'll start with the most basic, the similarity heuristic. The similarity heuristic describes when a decision maker compares potential events to similar known events to assess expectations for the future. This is an adaptive strategy where new information or observations can change the basis of assessing expectations. Such updating of beliefs based on experience can be formalized by Bayesian statistics, in which a given probability expresses the degree of belief about a particular outcome. Let's explore this. Say A is a proposition or hypothesis, and B represents evidence. Therefore, the probability of A is called the prior possibility, or the prior belief that A will happen. Probability of B is the probability of evidence, and it can be written as the sum over all instances of the probability of B given instance A times the probability of that instance A, also known as the total law of probability. The probability of B given A is the likelihood function, which is how likely is B to happen given A has happened. And the probability of A given B is called the posterior probability, which is how likely is A to happen given B has happened. This is what is observed going forward. Bayes' theorem says that the probability of A given B, which is your posterior probability, is the probability of B given A times the probability of A divided by the probability of B, or that your likelihood times your prior possibility divided by the probability of evidence is your posterior probability. Assuming evidence doesn't change, probability of A given B is approximately equal to the probability of B given A times the probability of A. And if B is completely independent of A, then the probability of A given B is just the probability of A. Updating priors means resetting your prior belief in probability of A, or probability of A is equal to the probability of A given B divided by the probability of B given A, where the probability of A given B, again, is the posterior observation that updates your beliefs for the next assessment. Here's some other behavioral or cognitive biases useful in economics, many of which add nuances to the similarity heuristic. The anchoring bias suggests a reluctance to update priors, while confirmation bias is the tendency to search for, interpret, favor, and recall information in a way that confirms or supports one's prior beliefs or values, or more formally, seeking evidence that supports your priors. Focalism is related, but describes too much attention on a single factor at the expense of other useful information. The availability bias describes where the ease in which events come to mind is taken as related to empirical probabilities of those events. This describes the subjectivity of priors. If one can't imagine something, it is therefore less likely to happen, while if one has direct experience of something, it is therefore more likely to happen. Vividity plays a factor with respect to cognitive availability and imagination, which is why videos are so effective at communication. Related to subjectivity or belief, the self-serving bias means you remember what you do more than what someone else does, like all my children each insisting that they do more dishes than the others. The actor-observer bias is interesting in that it has both a subjective and moral hue. One attributes one's own actions to external causes, a justifiable response, while others' actions are due to internal motivations normally framed as shortcomings. For example, an actor-observer bias would produce a claim such as people will only innovate if incentivized by profit, since they are fundamentally lazy and greedy. There's a couple of biases which describe the situational effects on decisions. With framing effects, people decide between options based on whether the options are presented with positive or negative connotations. With the endowment effect, people value items more highly once they own them and are less willing to give something up if it's already in possession than if it's not. For example, an owner's ideal selling price will likely be greater than a buyer's ideal paying price. Kahneman and Tversky, who we met in our brief historical tour of post-Smithian economic thinking, developed prospect theory, which describes how losses and gains are valued differently, and thus people make decisions based on perceived gains instead of perceived losses. If two choices are put before an individual, both equal, with one presented in terms of potential gains and the other in terms of possible losses, the gain option will be chosen. This can also be described as loss aversion. One consequence of prospect theory is the certainty effect, which demonstrates a flipping of preferences due to risk. Let's see what that looks like. So in the first scenario, when choosing between A, a sure gain of 30, and B, an 80% chance to win 45 or nothing, a vast majority of subjects chose option A, though the expected value, which is the amount times the probability, for the first is 30 because it's certain, and for the second is 0.8 times 45 equals 36. So the expected value of B is greater than the gain from A. When there is an option for certainty, risk aversion increases. If presented, on the other hand, with A, a 25% chance to win 30, and B, a 20% chance to win 45, more participants chose B. With no option of certainty, risk-taking increases, because the expected value of A is 0.25 times 30 is 7.5. The expected value of B is 0.2 times 45 equals 9. So B was actually the higher value choice. Thus we see that the preferences between A and B flipped in the presence of certainty. Myopic loss aversion describes the focus on short-term losses and gains rather than long-term losses and gains, which brings us to the curious impacts of time on behavior based on expectations, which I'll call intertemporal biases. George Ainsley studied the effects of time on decision-making. He observed that people prefer $50 now to $100 in 6 months, but do not prefer $50 in 3 months to $100 in 9 months. Both scenarios describe a doubling of gains in a 6-month time period. This is known as time-inconsistent discounting because the same preference is not applied to all time periods. It is claimed that rational people should prefer time-consistent discounting. Thus, intertemporal choice is a very interesting area of study. Let's look at 2 examples of present value calculations where you have an investment of V0, the initial value, and you expect a return of R% over a time period T, compounded n times per time step. Let's keep things simple and say that we're going to compound every time step, so therefore n equals 1. So we can say V sub t, which is the value at times t, is equal to the initial value times 1 plus r raised to the t. The initial value, V sub naught, is then V sub t divided by 1 plus r raised to the t. And we say the present value of an asset with future cash value, V sub t, is found by discounting that future expected value by a discount rate, expressed in this case as 1 divided by 1 plus r raised to the t. We've already seen that people actually use hyperbolic discounting. In using our example above, this would be expressed as V sub t equals V naught times 1 plus RT, which doesn't correctly account for compounding and is time inconsistent. Present value is then calculated as V naught equals V sub t divided by 1 plus RT. Therefore, the discount rate is 1 over 1 plus RT. Here's what that graph looks like. And we see that there is a higher discount rate farther out. Since people have a natural tendency toward hyperbolic discounting, they don't think in terms of compounding, and the now has a different valence than the future. Again, with the animal spirits, according to zoological studies, the same hyperbolic discounting tendency applies to rats, pigeons, and monkeys. Expectations arise for situations other than discounting of present values. When a firm plans production, there is an expectation of input prices and market demand outputs. When an employer hires a worker, she has an expectation of the degree of effort the worker will provide. These expectations are based on past observations of some kind or another, modified by any number of the biases above. Naive expectation setting is simply assuming the value at time t plus 1 is the same as observed for time t. Fancier algorithms employing recursive least squares estimates actually fare worse in an evolving system than the naive algorithm. Many of these relationships about which expectations are formed could be represented as functions. If the functional form is known, then expectation setting simply becomes a small set of observations that provide parameter values. If the functional form is unknown, machine learning algorithms that fit observations with non-parametric, nonlinear regressions can be helpful. For the observation and prediction of x, where x is between 0 and 1, neural nets are suitable. For x greater than 1 and unbounded, a random forest algorithm can be used. Let's look at a basic neural net. This neural net is going to be used to form expectations of an effort response function. So let's assume that we have an agent-based model with numerous households and a single firm. Each household will provide a particular amount of effort per hour depending on the wage. If the wage is higher, they'll put forth more effort. But each household has a different effort response curve for a given wage. The firm needs to set hiring hours and to plan production, so needs to develop an expectation of how much of an hour will be applied to production from the aggregate labor of the households. A sample effort response function will look something like this, where effort equals 1 minus the square root of d divided by omega minus the reserve wage. Essentially, the firm will set a wage and then observe the response from the households in terms of effort. A different wage will produce a different effort. We assume the firm doesn't know the equation, but they know there is a relationship between wage and effort, so the firm conceives of a black box, which we'll call Ada, our neural net, which models the relationship between wage, omega, and effort. Thus, the firm can obtain an expectation of effort, E hat, for any wage, omega. Here's the structure of the neural net, which is only a single internal layer, with an output layer and an input layer. And the algorithm learns the weight values that best predict E hat from observed omega values. Here's a time series animation of the evolution of Ada. We see that the model quickly resolves and that the model predicts effort will increase with wage. To adapt to changing environments, the model can be updated with a windowing method, where the model retains current weight values and refits to the last n observations. Individuals can also hold expectations about institutional or social arrangements that will affect decisions, even expectations about other people's expectations, which brings us to the anticipation of various degrees of average opinion, and we conclude again with Keynes.